Okay, well, let's get started. Next week's colloquium is going to be Young-Fu Lin from University of Texas at Austin, talking about Earth's deep iron, studied by inelastic X-ray scattering. Today we're very fortunate to have Leigh Orf from University of Wisconsin, Madison, to talk to us about supercells and thunderstorms, and he's got some very interesting videos to show us. He did his undergraduate and graduate work at the University of Wisconsin, got his PhD in 1997. He was at the University of North Carolina at Asheville for a number of years, and then at Central Michigan University. And he's returned to the University of Wisconsin just in the last couple of years. And after a lot of teaching undergraduates, he decided he really wanted to he was doing some really interesting research on the side. He wanted to make that his full-time subject. So now he's got some very interesting results to show. And thank you for coming.
And thank you for the invite. And I really appreciate the invite. And it's my first time I've been to Argonne. So again, thank you. And let's get this started. Okay, so I want to first acknowledge some of the folks I'm collaborating with. Bruce Lee and Catherine Finley both have lots of experience in field meteorology, going out and actually chasing storms and observing storms. I'm more of a modeler. But I wanted to acknowledge. And Robert Wilhelmsen, one of the pioneers of cloud modeling, three-dimensional cloud modeling. The work that I'm doing today is really just a really intense version of what he did and pioneered in the late 1970s, along with some other folks at the University of Wisconsin. So what I'm going to talk to you about today is my research on understanding the most devastating supercell thunderstorms. So if I had to sort of summarize what my research agenda is, I want to simulate supercell thunderstorms. These are a special type of thunderstorm with a rotating updraft that produce the most devastating tornadoes. I want to simulate those storms pretty much with as much resolution as I can, because of the fact that supercells and tornadoes especially, are rather small when you look at the scale of a thunderstorm, but we really need to capture everything to see what's going on with the tornado. I'm also very much into showing visual graphics of the model data. So in other words, as those of you who do modeling, doesn't matter whether it's subatomic modeling or if it's climate modeling, you have to save data to disk. And in my case, we're saving hundreds of terabytes of data. And I've spent an awful lot of time dealing with this huge data load and finding ways to visualize the data. But really what we're trying to do, and this is the truth for a lot of severe storms meteorology, is we just want to know why some supercell thunderstorms produce these long-track EF5 tornadoes. Think of Plainfield in 1990. I went to high school in Morris, Illinois. I actually played football on that field, and I remember seeing the aerial photographs of the devastated Plainfield High School and just freaking out. That was a nasty, very unusual storm, moved in a weird direction, wasn't warned. It was a great example of how we can improve our forecasts. So those are the kind of tornadoes I'm trying to understand. And the reason is because about 90% of the fatalities and most of the damage that occurs with supercells with tornadoes is these high end. So EF stands for Enhanced Fujita. Ted Fujita was another pioneer scientist at the University of Chicago. Go Illinois. He was one of the first scientists to go out and to look at the damage that storms left behind in order to try to learn about what kind of winds could have produced those storms. And he came up with a scale where he could go out and look at, say, you've got an oak tree that's 20 years old that had the bark ripped off. That means, okay, that's probably 180 mile an hour winds. That sort of losing these damage indicators to intuit things about the winds that cause the damage. So EF, Enhanced Fujita, we updated the scale. So it's there's more damage indicators now. We can supposedly get better information about the supercells by using this new scale and the different damage indicators. So EF4, EF5. EF5 is the highest category, okay? So that's the least common but most devastating supercell. And that's what we're trying to understand, because when you see a supercell on radar, it's already kind of too late in a sense. I mean, it may drop a very powerful tornado. We currently do not have the capability to predict with any kind of skill what kind of tornado is going to come out of a supercell, or even if one is going to form. This is just the way it is. So in order to do this work, you need several different things. You sort of need an overlap in computers and meteorology. You need a good computer model. In this case, we're running a model developed at NCAR, National Center for Atmospheric Research in Boulder, Colorado. This model is basically designed to do this kind of work that I'm doing. It's only about 10,000 lines of Fortran. I say only because I know some of these, some of the models out there add a couple of zeros to that. But it's OpenMP and MPI, as it should be. It maps pretty well to big supercomputers. I'm using the Blue Waters machine at the University of Illinois. So you need to have a good model. You need to have a good set of initial conditions. This is true for any initial value problem, right? An initial value boundary problem, you need to have a good set of initial conditions or your results will be meaningless or not very good. We ended up using some data from a forecast model where we could go into the forecast model and pull out the atmospheric column that defines the atmospheric sounding near a storm that actually formed, and then use that as our initial condition. So it's sort of a tricky way of getting observations. All the observations you can, they get folded into our forecast models, and then you can pluck out, say, a vertical column, and I use that as my initial conditions. Again, Blue Waters, it's got about 360,000 floating point compute cores, lots of disk space, lots of archival storage. Petabytes are no longer that exciting, right? You know, petabyte here, a petabyte there. And I spent a lot of time working on this part. And I don't need to tell you who do, say those of you who do modeling where you have a lot of data, where you have three-dimensional data or whatnot. But I/O can kill you. I/O can make your job go so slow that you can't actually get any science done. And I realized this about 10, 15 years ago. I started thinking about this as the supercomputing technology went from these large vector machines with shared memory to these distributed machines where you have to do MPI. You have the memory over here can't be distributed to the one over here unless you do some communication. So saving data I've spent a lot of time just saving data and organizing it in a way that is not too painful. And you do need a little bit of luck. I mean, when you do a simulation like the ones I'm about to show you, you don't know ahead of time what's going to happen. I mean, you can pretty much guarantee you're going to get a supercell, but you don't know if you're going to get a tornado. And I've done several simulations in this same environment, and sometimes I don't get tornadoes. And that's a very interesting scientific problem. It's also a very hair-raising forecasting problem because if you run the same model twice and get different results, that makes you wonder, it's the initial conditions. It's what Lorentz discovered long ago about the butterfly flaps its wings. So it wouldn't be a physics talk without some equations. So here's most of the prognostics. What I really like to focus on, what are we actually prognosticating in this model? We got the three components of the wind. We have water vapor. We have cloud, water, and rain. And then we have ice. So that would be snow, cloud, ice, and graupel or hail. Potential temperature perturbation from a base state. Everything when you initialize a model like CM1, you basically set it up as a horizontally homogeneous base state. So there's no variations in the horizontal. Then you perturb that, and then you're doing prognostic equations for the perturbation from that base state. And this is non-dimensional pressure. It can be easily converted into a regular old pressure. So I won't go through the forcing terms and such, but there's also for TKE there's an option to do forecast turbulent kinetic energy as well. So to give you a sense of the size of the problem, the simulation I'm going to spend most of my time talking to you about is about 2 billion grid points, 2200 by 2200 by 380 in a 120 kilometer domain, 20 kilometer in depth. I have an inner mesh that's isotropic, and that's been very important to have nice cubes instead of squashed rectangles or when you do these simulations, it's nice to have isotropic mesh. It costs you a lot, though. Another simulation I've done, it goes up to 8 billion grid points. So going from 30 meter grid spacing to 20 meter grid spacing, this number doesn't scale the same way. As we know, when you increase the resolution in a fluid code, you have to decrease the time step, and it's also in 3 dimensions, so you have 2 to the 4th, right? So 16 times more computations to double the resolution. So this is why supercomputers are so important. And I just kind of did a back of the envelope calculation. Over the few years we've been on Blue Waters, I've probably created a few petabytes of data with around a half a petabyte of actual data that has tornadoes in it. Not all of our simulations produce tornadoes, but there's still some good science in there as well. So the challenges for this work, this isn't necessarily in the order of the challenges, but getting the model to create the desired storm. That was the last challenge because I had spent so much time working on all the data stuff. I got that stuff worked out okay, but I didn't have a storm yet. But when I did get a storm, finally, to produce a tornado, I was ready. I had all the I/O code and all the visualization code pretty much ready to go. But just like the real atmosphere is not very proficient in producing lots of these big nasty tornadoes, neither does the model, and that's actually good, right? The model should reflect the atmosphere's not putting out these tornadoes very often, okay? So we get supercells, but we don't get the big long tornadoes, but we finally got one, and I'll show you lots of that in a second. In handling the data load, I've spent more time dealing with data than I've been doing science. That's going to change shortly because now I've got most of these things worked out. And visualizing is also very important. You can take the visualization stuff and then know where to go into it more quantitatively. Before I do supercells, I want to talk a little bit about non-tornadic supercells, partly because they also produce damage, partly because I did my PhD on microbursts, that I'd throw in a couple of microburst slides. So sometimes, here in Illinois, you get thunderstorms all the time. Most of the time, you're outside, maybe on your porch with a glass of lemonade or whatnot, and it blows through, get a little gusty, cools off a little bit, it's over. That's a normal air mass thunderstorm, an ordinary thunderstorm. In certain cases, those storms can produce some very strong winds. In fact, they can produce these downdrafts that, think of somebody just dropping something from a plane or whatnot, or a fluid, a cold fluid sinking, hits the ground and spreads out, produces a lot of very strong horizontal winds and a lot of wind shear. So the wind is changing over space and time very rapidly. The reason why microbursts were such of concern up in, say, in the 70s and 80s and 90s in the 90s when I was doing my PhD work was because microbursts cause planes to fall from the sky. If you're landing or taking off and you hit a big downdraft or you go through this little thunderstorm downburst, it can knock you out of the sky. And there's been some very high profile aircraft crashes due to microbursts. You haven't heard of any of those in like the last couple of decades because it's essentially a solved problem. We have terminal Doppler weather radars at all of our airports. All of our pilots are trained to deal with wind shear hazards, and the planes themselves actually have some sensors on that as well. So when I get in a plane, my least concern is a downburst. And I'll let you think about what the biggest concern would be. There's been some interesting things happening on planes lately. So anyway, I wanted to show you at least one slide. So this is from a paper I wrote a few years ago with some wind engineers at the University of Western Ontario. They're interested in improving the models that engineers use to understand how the wind load can affect things like buildings and power transmission lines, okay? Their models are pretty brain dead because they're not meteorologists, and that's not like a slur against engineers, but they just don't have the physics right. And I'm trying to do the brute force approach where I actually simulate an entire storm that produces the rain that then produces the downburst, and then using that as to feed into a building or a power line or something. So this is not the kind of storm I'm going to talk to you about today. Here's a little movie that shows this in motion. So there's this cold blob of air that descends from the sky. We're only showing the potential temperature perturbation. Notice how it kind of spreads out into a cold pool. The idea of a cold pool is very important to supercells, so just kind of keep that in mind. In this case, this is pretty much straight line winds. Right about here, the storm's kind of moving towards this part of the screen, so your winds tend to be strongest right there. You get winds in excess of, say, 80 miles an hour, but they only last a few seconds, and then it's off and gone. But this cold pool, keep your mind on cold pools because they're going to play a very important role in storms like this. So this is a supercell thunderstorm. Here's a big wedge tornado underneath here. This is the reason I use this to use as an example is because this line of clouds here, this region, this is called a tail cloud, but notice how it looks like the tail cloud is kind of feeding into the supercell updraft, which is right above the tornado. We've identified a feature that's kind of associated with flow like this that I'm going to show you quite a bit. This here is rain in the forward flank of the storm. We meteorologists split supercells up into a forward flank, that's where they're going, and a rear flank, that's where they've been. Here's the rear flank of the storm. Right here, this is rain falling in the rear flank downdraft region, and this is the forward flank downdraft region, and there's our big tornado. So this is the kind of storm we're interested in. This was, I think, an F4. Now this is a volume rendered image from one of my simulations. And I show this to give you a sense of the scale of the problem. Here's this isn't even the full domain. This is only a small part of the domain, but you have to get this all resolved in order to resolve this little tiny tornado, which is about 1 kilometer in diameter, okay? And here's that tail cloud that we have in our Model 2 in a wall cloud. We're seeing all the similar features. We haven't put any precipitation in this figure, otherwise it would obscure some things, but this gives you a sense of the scale of the problem. We have to resolve that tornado pretty well. So a primer on supercells. This is just a sort of a diagram showing the different components of supercell thunderstorm, of an average supercell thunderstorm. So here again is the forward flank of the storm where it's going. Here's the rear flank where it's been. Here's this funny looking tornado thing. This is the rotating updraft or mesocyclone. So this is one of the components of a supercell. You have this air that's rotating, not like a tornado, over a much wider diameter, but it is very important. And the rotation in the mesocyclone, where does it come from? Well, in the upper part of the storm, it comes from simply tilting the environmental vorticity that's already in the atmosphere. The type of conditions that lead to supercells, when you look at the environmental conditions, we have a pretty good idea of what those are. You need to have a lot of atmospheric wind shear, so the wind is changing direction and speed with height. And you also need a lot of moisture at the surface and instability, and then something to kick it all off. But this rotating updraft is what discerns a mesocycle, or discerns a supercell. Storms that don't have rotating updrafts aren't supercells, and they tend to only, if they produce tornadoes, very weak ones, very transient ones. I'm going to spend most of my time talking right here in this region of the storm. But this funny looking thing here is denoting the front, the forward flank downdraft, a gust front or boundary. This is the boundary between the cool air that is formed by the evaporation of rain, the melting of hail, thermodynamic processes. This is extremely important. This cold air, when you have this cold bulge of air adjacent to atmospheric air, which is warmer, it produces horizontal vorticity. So supercells are all about spinning, all about vorticity, which is just del cross V, right? That's vorticity. So you've got this boundary, and it turns out that interesting things happen at this boundary, especially when you have this really strong updraft parked right over it.
The typical scale.
So you'd be looking at, like, say 20 kilometers across here, so in this visible image, maybe a little long, maybe a little bigger. The tornado itself is probably a kilometer or so. So, if you look on weather radar, in fact, I'll show you some weather radar very shortly.
They always rotate the same direction.
Good question. No, we have, in fact, and I don't want to get too far into this, but when a supercell forms, it typically splits into two supercells, one rotating in one direction, one rotating. In the southern hemisphere, they rotate in the opposite direction. That's actually true. It has to do with the fact that, you're in the southern hemisphere, the thermal wind relationship and such. So yes, but in the northern hemisphere, when you look at a supercell, it's going to be rotating cyclonically, almost always in the U.S. So this is a radial velocity. So the radar is over here somewhere, and we have this couplet. So we have this screaming motion towards the radar, screaming motion away from the radar. We can intuit that that's rotation. Here is the reflectivity. This sort of bullseye here is probably what's called a debris ball. This storm has probably kicked up enough debris that it's reflecting a lot. So the hook echo, this storm is sort of embedded in a line of other storms, but this is the supercell right about here. And this storm that occurred on 24 May 2011, we captured the environment adjacent to that storm and simulated a storm in this environment, and we got something that looked similar to it. I want to be clear, I'm not saying I'm simulating that exact storm. Here is our radar reflectivity, which we can calculate from all the hydrometeor variables. So here is that region I was pointing to. Here's the hook echo, and this swirly thing here is the cyclonic tornado. We actually get an anticyclonic tornado. It rotates clockwise in this simulation. And anticyclonic tornadoes, the ones that rotate the other way, are rare, but certainly not unprecedented in right-moving cyclonic supercells. So that's another interesting thing to study once we figure out the other tornado that's more powerful. And here's a zoom in of that same region. So right here at the time of this image, we have a tornado right here. You can sort of imagine the air spiraling into this. This is 1 kilometer above the ground, I think. And you can sort of see how this one's rotating in the opposite direction. So I really haven't spent much time on the southern one, but the northern one, I'll be showing you quite a bit of imagery from that. I wanted to show you a little bit of real tornadoes first before I dive into the simulation data. My collaborators are avid storm chasers. They go out, they do this recreationally, and they also do it professionally if they have the funding. Bruce and Kathy were members of TwistX. TwistX was a field program that Tim Samaras, who perished in the 31 May 2013 Oklahoma 2.6 mile wide crazy ass tornado from that supercell. That was just a bad storm. I'm going to try to simulate that one as well. But anyway, I'll show you some different things. This is from Pilger, Nebraska. There was several supercells, several tornadoes. It was a crazy event. You'll see some different morphologies. I want to show multiple vortices because tornadoes often have multiple vortices, and watch as it transitions to these different things. So I'm speeding this up a little bit. If you focus down here, you'll notice this is, you see these individual vortices. They're showing up in the cloud field because the pressure drop inside due to the spin will be, you'll see condensation. Notice these clouds moving in towards here from the right. This is kind of a region I'll be spending a lot of time in. This is in real time. Now it looks more like a stovepipe. You know, meteorologists and storm chasers have all this lingo. You can even see a little bit of maybe hail on the ground there. Is that water? And here, this is an interesting event. So this storm had 2 tornadoes. You can see how debris is being centrifuged outwards. That's something our model is unable to do at this time. That tornado right here ends up merging with another one in a future slide. So these guys are pretty close to the storm. You can see debris spiraling outwards. Yeah, this guy's just like, oh, ho hum, it's just a tornado. It's Nebraska after all, you know. Just another day in Nebraska. But yeah, there it goes. This is the kind of storm we're trying to simulate. You know, not the low-end, typical short-lived tornado, but the really big, nasty one. So this is again sped up. This is the tornado we've been looking at. This one has gotten stronger now, and you'll see this thing actually come in. It's, sorry for the shaky vision, nice lightning shot there, but watch this guy go get sort of sucked into that. So all these different things I've been talking about, we see aspects of this in our simulation, okay? Now this is a different storm, different environment, but you can at least get a feel for what is going on. So now I'll get down to the model stuff. So this is a volume rendered image that is the entire model domain from say 100 kilometers or so, and you can barely make out the tornado. You can see the overshooting supercell, the thunderstorm top. This is something we see in radar image or satellite imagery all the time. This is a back-sheared anvil. This is the anvil. You can see some mattis clouds. It has all the good stuff in it that you'd expect to see. And I'll kind of this is just a little sequence that sort of gives you a sense of the scale again. 120 by 120 by 20. I do use a vertical stretch out here in the nether regions to save some computation, but the grid in this region of the storm here is 30-meter grid spacing. It's isotropic, 30 meters in each of the 3 directions. So that's what we're trying to do. So I'll describe the next 2 slides, I will just sort of describe what to look for in the animations. So it's one of the big questions in meteorology is why do tornadoes form? We call it tornado genesis. Just what are the conditions that lead to that tornado forming? Because most supercells don't produce them. So tornado genesis, what's happening in our simulation when the tornado is forming? There's some very interesting flow structure that shows up in the model. The cold pool I've been talking about actually has a very interesting vorticity profile. It's almost like you have a sheet of vorticity that's a couple hundred meters deep. That is what we call streamwise vorticity, when you have the wind vector and the velocity vector pointed in exactly the same direction. When you have streamwise vorticity, all you have to do is tilt it to get rotation. If you have crosswise vorticity, you end up getting like a hairpin or a couplet. Okay, so think of the 2 vectors. You know, if they're normal or orthogonal, or if they're aligned along the same region. Streamwise vorticity, they're aligned in the same region. So we have another feature that also shows streamwise vorticity. It's in the cold pool, but it's sort of like a rotating tube of cool air. We call this the streamwise vorticity current. We gave it a name because we just had to give it a name because it's so prominent in these simulations. The tornado forms just kind of, you'll see a lot of small vortices that occur before the tornado. You'll see the updraft gets stronger, and then the tornado just descends down like you see in the field. And in fact, one of the things that is gratifying is that some scientists have gone out on this storm. They brought their stuff out, their radars and such, and some of the features they saw in the storm that I'm essentially trying to simulate are similar to what I'm saying. Now you may think, well, duh, right? But it's not duh, because there are still some theories about tornadoes, about how they form. Is there a dynamic pipe effect? Some people think that. We're not seeing that. Do they form from the top down or bottom up, or is it kind of simultaneous, or is it at the same time? These are the questions that people are trying to figure out. In fact, the vortex seems to pretty much form along its length almost simultaneously, and that is what was actually seen in the field for this particular storm. Tornado structure. Tornadoes can have, like a hurricane, can have a downdraft in the center of them. That's called a 2-celled structure. But oftentimes when tornadoes are weak or just forming, at least in my simulations, they have an updraft throughout the whole depth of the tornado, so they're a single-celled structure. So you can go from a single-celled structure to a 2-celled structure to a multiple vortex structure, where now you have many vortices sort of orbiting one another. And we actually see that progression in our simulations. Okay, so let's show some movies. So this is the cloud field, this is the rain field. And this is right about where you want to pay attention. So this is 1 frame per second, or 30 frames per second, but one different image for every 1 second. I save data every 1 second. So people don't normally do this because of the data load. So we can see how, here's the surface here is the buoyancy, so cold is blue, and the air ahead of the storm is this color here. So notice these tiny little tags kind of hanging down there. Those are potentially showing you where some vortices are, and then, oh, there we go. There's our tornado. Now again, this is 30 times real time, but that looks a lot like what happens in the real atmosphere. It does. So what I'm going to do next is I'm going to go back and show that sequence again, but I'm going to throw these other things up here. I want you to focus, this is the updraft, so this is the W component of the wind, 1 kilometer above the ground, this is the radar reflectivity, and this is the surface cold pool. So what I see is this region gets really red here. That means the updraft at 1 kilometer, which is right about here, is getting super strong. And one of the ways to grow vorticity is to stretch it. And the stretching term has this dW dz. So if the vertical component of the wind is very strong at 1 kilometer, it always goes to 0 at the surface because you can't have air go through the ground. So you have a lot of stretching. And I think that's one of the things that's important. But you'll notice this air that kind of streams in from the right and kind of wraps around. That's associated with this tail cloud, but also maybe this Streamwise vorticity current thing that I'm going to show you next. Anyway, this just goes on. The tornado undergoes some interesting morphological things we haven't really looked at yet, but you can certainly see it in the cold pool. You notice this is something that I'm not sure that people really see in their models. The updraft is parked right above this colder air. And it's pretty intuitive, but it's harder to lift cold air than warm air because it's more dense, it takes a little more force. But this storm doesn't care. The updraft is so strong, it's happy to lift that cooler air. Also, this boundary here is generating horizontal vorticity that's getting tilted into the vertical that I think is helping to make this updraft even stronger than it would be through pressure gradient terms. In meteorology, typically when you have a rotating vortex, it's a center of low pressure. Whether that vortex is rotating parallel to the ground or normal to the ground or anything in between. So there's low pressure regions that are associated with this Streamwise vorticity current that I'll show you in a minute. But now this thing's just going and going. What's that?
How large is the vortex?
The vortex here, if you just look at the cloud field, it's a little over a kilometer. But if you look at the individual vortices, it's more like 500 meters or down to 100 meters even. So when I show you the individual vortices, you'll see, you can kind of see them here. You can see some of that structure in there, and the cloud, there's a little vortex that kind of streams around. You see a lot of that multiple vortex stuff. Eventually, one of the things our model needs to have is a centrifuging term because the tornado gets filled with rain. This 2-celled tornado has a downdraft in the center of it, and some of the rain gets captured in there. It should be flung outward. That's some physics that needs to be put in the model. But I don't think it really affects our solution too much. I mean, I don't think the storm doesn't really care, is what I'll say. And as far as getting the tornado just right, maybe we didn't get the tornado just right, but this is pretty right. I mean, no one's really done this kind of work before. So as it occurs in nature sometimes, this thing gets wrapped in rain. I've tried to render both fields to make it look realistic. Now what happens in this case, if you're chasing this storm, is that you don't know where the tornado is. Rain is falling all around you and blowing around, and it's very dangerous. Again, the chase lingo of rain-wrapped tornado is not something you want to hear because it's just lurking in there somewhere, but it could be a very strong tornado. Joplin, Missouri was a rain-wrapped tornado. It was very wet and you really couldn't see much, and that was a bad storm. But you'll notice as things go on here, the downdrafts, this blue everywhere now, so you have downdrafts everywhere. It's probably associated with all this rain that's falling. There's still a signal of a tornado in here. I need to run the model a few more cloud minutes to kill it completely. But essentially, it's pretty much dead at this point. So I will show the same sequence again, but I'm going to render the updraft using volume rendering. You start to see the updraft right around 6 or 7 meters per second. But do the same basic thing before, only now this is the cloud field. Here's our buoyancy, and here's our reflectivity. Notice the top, I've clipped the field here. You'll start to see yellows showing up here, kind of like where I had the circles on the earlier frame. And this is right where the Streamwise vorticity current is that I'm going to show you. So this seems to be important. Once this updraft really gets stronger, you're going to start to see, you don't see it as well as in the cloud field perhaps, but there's your tornado. This is just W. So this is up, and this is up faster. And you will see blues. When you start to see blues, those are downdrafts, okay? But notice right around when the tornado forms, it's mostly updrafts. You see the reds and the browns and the yellows. The blues start to kick in as the rain starts to fall more. But this thing is just parked right above this boundary, this cool air, warm air boundary, and that seems to just be providing enough vorticity in the horizontal that when tilted and sort of converging and amplified, it essentially wraps up into the tornado. I mean, in this simulation, the cold pool essentially is the tornado. If you just kind of trace these parcels backwards, they all pretty much originate from the cold pool. And this hasn't always been something that has been widely accepted, and I'm not saying that it's always this way because this is just one simulation, but it's an interesting result. Now, you'll notice now that the tornado's gotten wider. You'll notice how you have a really strong updraft near the ground. These are from surges. When you see the updraft get close to the ground, you've got these downdrafts sort of spreading out the storm, and it causes like a horizontal roll, and you'll see the updraft, get stronger. But that's just from that sort of straight line winds that are coming from the rear flank. Now it's really chugging along. You've got multiple vortices you can see. It's chaotic, to some extent, and it just goes and goes and goes. But yeah, this is pretty cool. I mean, we've really never had this kind of data set before. So I can go back. I've saved data every 1 second, and I can sort of do all sorts of things like drop air parcels, do Lagrangian parcel analysis where you just follow the air around and look at the forcing terms on it. This is how meteorologists try to figure out things like supercells and tornadoes. Where is the air coming from? Where is it going? And what are the forces acting on it? And then we can step back and say, okay, can we somehow use this new information to understand how to forecast these storms better? Because again, we don't understand tornadoes very well. Okay, so we have to understand what we're trying to predict. It's hard to predict something that's completely, a mystery, right? It's very frustrating. So we need to do many simulations like this, actually. Okay, so lots of eye candy for you. Now, this next sequence is vorticity. So let me pause it and sort of talk about what I'm showing you here. This is that updraft at 1 kilometer again, okay? So here's that. You're going to see this area get red again. We're looking southeast, so we're looking from back here this way in this field. What I've done here is I've taken vorticity, the magnitude of the vorticity, okay, just the magnitude of the vorticity vector, and I've shaded it by the vertical component so that when you see reds, that's cyclonic, that's counterclockwise in the vertical. When you see blue, it's anticyclonic or clockwise. So we can tell blue guys from red guys. You've got rotation that goes like this, you've got rotation that goes like that. And you can certainly see that this is a cyclonic, as you'd expect, a cyclonic supercell, but we do care about what's going on in the rear flank as well. When you see gray over here, this is horizontal vorticity. So what's cool is when you see the gray go to red, you're seeing vortex tilting. You're watching it happen. The updraft, as you can see, the air is going up. You're in this big updraft. There's plenty of stretching as well. So at some point, we're going to just call this thing the Streamwise vorticity current. And I mean that sort of not really glibly, but it really hadn't formed in a while. You see some interesting structure near the ground. There's your tornado, just kind of, there it is. I'll show you some different angles on this as well. And you see how the updraft has gotten strong. So I'm really keying in on this low-level updraft. I've just changed the angle of view. Now we're looking southwest, looking this way now, sort of along this feature. And there's your tornado. You can see how the updraft is so strong it almost peels vorticity off the ground. That blue guy right there just came from near the ground. You can see how the blue vortices get sort of wrapped around the cyclonic tornado. The tornado tends to sort of reorganize those and send them up into the stratosphere, whereas the cyclonic vortices just kind of merge and get assimilated into the tornado circulation. And here's that vorticity current. So this is decoupled from the tornado, and this is the feature that I'm really interested in, because I think this is helping to do that, is helping to do that. I think that's kind of the relationship. There's a feedback of some sort between this air that has low pressure. It's actually increasing the vertical pressure gradient in this region that is helping to make the updraft strong, that's helping to drive the tornado. But we haven't put all the pieces together yet. And notice that little blue guy there, that's the downdraft in the center of a tornado because it's a two-celled tornado. It eventually gets multiple vortexes. You can see a whole bunch of little guys going on there. But yeah, this thing just crunches on. Here's that the rear flank of the storm is starting to kick out a lot of precipitation. A lot of it maybe came from the forward flank and kind of wrapped around. But you'll notice this blue intrusion here. Once this blue, this is downdraft air, it kind of erodes the updraft, this low-level updraft. And eventually, you can tell the tornado's fighting for its life. It's getting sort of crushed, well, I wouldn't say crushed, it's getting kind of pummeled by rain and negative buoyancy and other things. Again, we have to unpack all this. We haven't done that yet. It recovered pretty well from that one intrusion, but now you're going to see a whole bunch of stuff kicking out from the rear flank of the storm, some of which maybe even originated over here and kind of wrapped around. This rear flank is a place where meteorologists spend most of their time studying, because the leading theory of tornado formation is that downdrafts over here can initialize a tornado over here. Interestingly enough, we don't see that in our simulation. Everything we see is going on in the forward flank of the storm. Now you can tell how downdrafts have kind of persisting. This is all blue. You can see how everything's kind of spreading out as the air hits the ground and spreads out, kind of like a downburst. Not really, and then it just kind of gets crazy. This is all vorticity generated from all this rain, and things are getting really rainy. And this is kind of how supercells often go. They often go for a while. They get really, really wet, and you know, things get disorganized to the point where the tornado can no longer be maintained. So here's a view of tornado genesis from 4 different zones. We've kind of looked at this one. So this is an interesting view. Here's these little red guys coming in from the forward flank. These aren't tornadoes, but they're little vortices that are helping to bring vorticity in. It kind of wraps around. This is a good view here. After you start to see this wraparound effect is right about where you start to see the tornado form. And then you'll just see a red guy. There it is. There it is. There it is. There it is. 4 different views of tornado genesis. Now, when I look at that, I don't see any magical smoking gun. I see a whole lot of different things kind of coming together, and it's certainly not something that's going to be, I think, a super easy theory of tornado formation. I think there's a lot of things that have to happen, at least for this type of storm. So let me just do a few still frames here. This stands for cyclonic vortex. This is from the simulation we published. This is the tornado here. It's already formed, but these guys can just simply provide vorticity to the tornado. You'll see a 2-celled structure with maybe vortex breakdown, so there's a downdrafting here. And these anticyclonic vortices will often kind of get wrapped around the tornado and advected upwards. So they interact in a very interesting way with the cyclonic tornado. Here's a later on. That one that we just showed you, it's now a horizontal vortex. It's been tilted. You can see this nice little hairpin vortex. So essentially the tornado is just taking that vortex, did all sorts of nasty things to it. You can watch it go up into the upper part of the cloud. Sometimes you get anticyclonic vortices along this boundary. It's kind of like a vortex sheet, a vertical vortex sheet, but a theoretical vortex sheet should only have one sign of vorticity. It should all be cyclonic. So what I think is happening is, you know, way in the forward flank of the storm, you've got rain and hail and all sorts of things going on. And you create a little vorticity this way, that way, and eventually it comes in, it gets amplified, and you just sort of get these pools of vorticity that once they get parked under this really strong updraft, they start to organize. So some of them are negative, some of them are positive. More of them are positive than negative, which is what you'd expect for a cyclonic tornado. But we haven't done a study of where all the vorticity is coming from. We're just getting the quantitative aspect of this research going. So this is the thing we're calling the Streamwise vorticity current. Here I am, this is just vorticity magnitude. I'm not shading it by red or blue. This is just vorticity magnitude, so some of these are anticyclonic. But this is just kind of a good shot of right about where the tornado starts to form. This vortex right here is going to be the lucky guy that becomes a tornado. The Streamwise vorticity current is this sort of horizontally rotating tube that gets tilted into the vertical. And some of the animations I've shown you have hopefully brought that across. We're very hesitant to give something a name. You know, when you name something in science, you have to be sure that you want to, you know, it's got an acronym now. You hope that it's going to be out in nature, because this hasn't been seen in nature yet because we haven't looked for it. But this is kind of a good diagram of what's going on. Very strong updraft, peeling vorticity off the ground from the cold pool. It's being organized. It's being brought into the bottom part of the mesocyclone, but you have all these small vortices too that are sort of accumulating and coming together to produce a cyclonic tornado. And near the surface, you don't see it, is the Streamwise vorticity sheet near the ground. So all these different fascinating flow features that we're going to be diving into to try to quantify. Here's another shot looking at the Streamwise vorticity magnitude. This is that Streamwise vorticity current, which again is not directly interacting with the tornado, at least near the ground. You have to, even up in the higher part of the cloud, it seems to wrap around the tornado. Very interesting feature. I think it's important. I think something like this is probably in the real atmosphere. This is a very dangerous part of the storm to study, though, because If you're in this part of the storm, the storm is actually coming right for you. So if you're in the Streamwise vorticity current region, a tornado might be coming to your location very shortly, which is not a place you want to be. Just going through, this is just showing very painstakingly the first time I could trace the vortex that became the tornado. Here's an anticyclonic one, so here's that accumulation region. A couple, 2 minutes later, here it is there. I'll just let this go. This is figures from the paper we published on this work. But you can see that, at least when I look at this, I don't see any smoking gun. I don't see anything that just kind of screams, that's what caused a tornado to form. You see this one vortex, this sort of wraparound is what I find interesting. There's something that kind of happens where this really starts to kick out, all this space kind of clears out, which is what I find interesting. But there it is. Now, at this point, it's a tornado. And there's that SVC. It's been there all the time, but I just marked it there. If I just release parcels near the ground, this is what happens. So these parcels are all very close to the ground. And you can see two different things. You can see your tornado, cyclonically rotating tornado. This region, this thing here, that we're calling the Streamwise vorticity current, or at least a piece of it. And over here in the rear flank, you just see this typical gust front where the air ahead of a storm is bashing into the cold air and being forced upwards. But you also see the anticyclonic rotation on that side too. So all this cool stuff going on. If you sort of just take the SVC and look at it like a plan view, you sort of squash the third dimension out of it. This is kind of the trail it's taking. Here's the tornado, here's the SVC, this is the hook echo. And our tornado's full of rain. It probably shouldn't be, but we'll fix that later. Let me now show you the SVC in even more detail. If you just release parcels, just release them, this is what they do. You can tell that it's rotating. If you look at that, you can see right there that there's rotation going on, right? I mean, it's very clear. That rotation is this way and it's going up that way. This is the rear flank, the forward flank. So this thing here is really probably the most exciting thing that I've discovered in this simulation, along with the tornado, of course. But it's a new flow feature that really hasn't been seen before. And here it is again, just trying to give you a three-dimensional view of it. It's helically flowing air that's actually moving kind of like a helix in itself. So lots of rotation. And there's your tornado in the middle there. So that SVC thing is something we're going to really pay attention to. This is a sequence that was created by David Bach at the National Center for Supercomputing Applications. I just love this. He really shows the cloud very well. This is the overshooting top. He's only showing the cloud, no rain. There's the big, you can see these lovely features. You can see mammatus clouds. There's a tornado. Here's the mesocyclone and the updraft. This, to me, is the best rendering of a supercell I've ever seen in my life. He's done a very good job. He's taken my data, and he has his custom-built renderer that just does a really nice job. This picture, I could watch that for days. Here, again, is the Streamwise vorticity current, releasing parcels along this boundary, and just watch them go. There's your rotation. It's pretty undeniable. Notice how the parcels of the vorticity are pretty much taking the same path. It's Streamwise. On the aggregate sense, it's definitely Streamwise. Here's our tornado just doing its thing. Here's vortices kind of spinning around. But this thing is where we're going to be focusing a lot of attention. This isn't like a new concept, the idea that baroclinically generated horizontal vorticity can get tilted, but the structure we're seeing, when you really get the resolution higher and higher, you start to see features that sort of they converge to a really interesting solution. So there it is. There's the SVC. Here I just look at during the maintenance phase of the tornado. You see the same basic structure, so our tornado's going pretty well. Here's a cyclonic, anticyclonic, cyclonic, anticyclonic, cyclonic, anticyclonic, cyclonic. Notice the red ones tend to be a bit stronger than the blue ones, but these blue ones, they get sort of pulled up and advected upwards, whereas the red ones just kind of assimilate into the tornado. But what I'm getting at here is this regime, this flow pattern doesn't really change that much over very long periods. This is the point at which the strongest horizontal wind at the ground is found in the simulation, 143 meters per second. That's over 300 miles an hour, probably 320 miles an hour, at the interface of this little anticyclonic vortex and the main tornado. So that's instantaneous winds. We should probably be talking about 3-second average winds when we do tornadoes, because in a model, you just pick the maximum velocity may have only occurred for a fraction of a second. But we get some very strong winds. This is like 40 minutes later. At this point, you can see how the SVC is weaker. It's more transparent because the magnitude of the vorticity is less. You're still getting some cyclonic and anticyclonic guys, but the rear flank is kicking out all this vorticity, and this is where it's starting to get sort of enveloped in rain. Yes?
Is the SVC indicative anyway of the tornado track?
Basically the tornado track is going to be more a function of the atmospheric parameters before the storm even forms. We can with pretty good fidelity predict the direction of the supercell and hence the tornado. The tornado is always attached to the supercell and we can predict the supercell movement. But tornadoes do funny things sometimes. They take funny paths. I wouldn't say that the SVC is a good indicator of the tornado path. Now, I want to make another thing clear. When I've been showing you all these animations, we're moving with the storm. The storm is actually moving like at 35 miles an hour to the northeast. The model domain is moving with it. So it looks like everything's just parked on the ground, not moving, but it's actually moving. So no, I wouldn't necessarily say it's easier to see a tornado than an SVC, and you might as well, unless there's different kinds of SVCs from different directions. We haven't done any more simulations in this environment, so I don't really know. But mostly I look at the SVC as an indicator of a potential mechanism, a potential flow feature that can help to make a very strong updraft near the ground, which is, I think, crucial for these very long track tornadoes. So let me show you the tornado at that point where it's showing 143 meters per second winds. On the left is the vorticity shaded by the vertical component, and the middle is the downward component of the wind to show you the downdraft in the center, and on the right you see the pressure deficit. So I'll pause it right there. So here's your tornado. You can see sort of a little bit of the SVC. I've clamped the threshold a bit higher so we can see the tornado better, but you can definitely tell there's some vorticity there. This is the downdraft in the center of a tornado. It's two-cell, that's important to meteorologists. But this is what I find very interesting. So as you know, tornadoes have centers of low pressure due to the fact you have essentially a cyclostrophic flow balance where the pressure gradient and the angular momentum are balanced. But this thing here is pretty much where the SVC is. So I'm thinking that, it's rotating like this. It's probably dropping the pressure in the center of it. But when you have this negative pressure deficit, you have a very strong pressure gradient. When you have a very strong pressure gradient, you have very strong winds. They may not go along that gradient exactly because there's other forces, but this feature here, we really need to figure out what's going on because I think it's really it's important. And also this tornado goes up. This is only up to 10 kilometers, but this thing goes up to you can see a signature of a tornado up to almost the stratosphere, almost to the tropopause, not quite the stratosphere. So another question meteorologists have: how tall are tornadoes? Well, this one goes pretty high. They're not shallow. Here I'm releasing parcels to see where the air is going. Here's air that's along that boundary, so you see the SVC air. This is air that's in the cold pool, the dark green, and it essentially pretty much becomes the tornado, which I find fascinating. Yellow is going more towards the rear of the storm, and the blue is the rear flank. And I'll slow it down a little bit. You can see the vorticity right there in the wind field, right? You've got these plates of sheets of paper that are kind of spreading apart almost. That's indicative of some very strong horizontal vorticity, but watch what happens. It gets tilted, and then bang, it's the tornado. So, this is an interesting approach, and what we can also do is not just trace the parcels, but trace the values of different things along those parcels. So we can, look at all the forcing terms and things like that. And I'll do it one more time just to show you that. Our tornado is pretty much fed from air on the cold side, and it kind of makes sense when you think of where's the vorticity coming from. It's pretty much coming from the cold pool. At least in our simulation. Again, I don't want to make too many generalizations because, as you know, it's one simulation, one environment. We do need to do this in more environments to learn more about what's going on. And yeah, here I'm just releasing parcels at about 1 kilometer above the ground. And this is cool because what happens is in that downdraft, parcels essentially get trapped in the tornado. If a parcel just gets advected a little off to the side, it gets slurped back up again. So essentially you're confining the parcels in here. It's the air that's coming down, and some of these are getting sucked back up again. I've colored them by their vertical components, so you'll see blue and red. The red is sort of on the outside where it gets slurped up on the outside of that boundary of the downdraft. And here, I'm just looking at the surface vorticity, so blue and red. So here's our cyclonic tornado. It's very chaotic. Some of the vorticity is coming from the cold pool itself. A lot of it sort of accumulates along this boundary here. And I'll just kind of, for the sake of time, skip ahead. But if you think about it, if we need to get forecasting right, that's going to be hard because every little vortex here is, you can't predict that with any fidelity, especially when you've got, terrain. There's no terrain in this model. We don't have buildings. We don't have, variations in topography. So, there's a lot of chaos in these simulations, which is one reason I think for the forecasting problem, we need to do not just single simulations, but we need to do dozens of simulations, do ensembles of simulations, and then derive statistics from that. Anyway, so I'm kind of wrapping up. There's one more simulation I've done. We have to kill this tornado first. Let me kill this tornado. So this is the one that we published. This is the tornado decay phase. This is the updraft in sort of gold. Blue is the downdraft. This is the tornado in the vorticity field. Here's the rear flank of the storm where the rear flank downdraft is. So the tornado's doing okay, but look how all this blue. So there's this super strong downdraft that just about pummels this tornado into oblivion. And I suspect that some of this is forced by the rain that's falling in this region, but some of it's probably due to pressure gradient forces that we haven't identified yet. Okay, so this is the 20-meter simulation. So I've also done a simulation in the same environment with slightly different parameters, but at higher resolution. So this is the 8 billion grid point one. And this one actually produces a really nice multiple vortex tornado. This is an anticyclonic tornado that kind of decays. And we'll eventually study you, but okay, this is 60 times real time, or 30, I forget which. I think it's 60. So here's, this looks really good. But again, it's sped up really fast, so don't think that you'd see this out your window. What I'll do is I'll slow it down, and I'll also put it up against some actual side of the road footage of the tornado that happened here in Illinois, the Rochelle tornado from 2014. Some guy got stuck on the side of I-39, which I just drove down a couple hours ago, and basically filmed it. He didn't know what to do, and he was very lucky. He was very close. But so you'll keep an eye. But notice, you're seeing individual vortices now. This is just the cloud field. I'm not doing anything fancy here at all. I'm just rendering the cloud field. So as you get to higher and higher resolution, you really start to see more physically realistic things going on, which is what you'd hope, but it's not always the case. So this is a Fairdale, whatever you want to call it. Yeah, this poor guy is like, oh, I don't know what I'm doing, but I'm going to film it. Thank you. I appreciate that. I'm glad you're alive. But the reason you'll see some little, you'll see daylight between the vortices. There's one right there. You can see the multiple vortex nature of this real tornado here in one right about here. Yeah, he got real close. There's one right there. So we're seeing that same thing. And again, that guy was really lucky, and he's okay. Let's be glad for that. So, and here's the vorticity field shaded by the vertical component for the 20-meter simulation. I've just changed the threshold for vorticity here, so you really can see the structure, the internal structure of a tornado. You see how it's got these twin rotating vortices. That's the two-celled model. Now near the ground, it's even more complex, and I'll show you some slices at the ground shortly as we wrap things up. But and this is just a lower threshold for the vorticity magnitude. So you're seeing more lower values, just playing with thresholds. I want to be completely clear, And here's just the surface pressure deficit. So we're just looking at pressure here. Angry swarm of blue guys kind of going around one another, and also some other longer period oscillations. This is vorticity. So I'm animating a little bit fast, but you can see that it's pretty chaotic. Primarily cyclonic vortices in a very chaotic manner. In a multiple vortex tornado. And I saw some actual, at the Severe Local Storms Conference in November, where I presented some of this work, I saw some actual field data from the 31 May 2013 storm in Oklahoma that looked just like that. So these multiple vortices and such, I think we're on the right track here. We're getting some of these details right. So my parting thoughts, we can now do these simulations where we have a full supercell thunderstorm, and essentially we're running at resolutions that are getting closer to like earlier chamber studies where people just made a little chamber model of a tornado. And that's pretty exciting because the chamber models that are used are useful in looking at this sort of tornado structure, but you impose the updraft and there's no feedback, there's no cold air, it's just all barotropic and it's not very realistic. So being able to do this is my interest, is getting it as right as we possibly can and then sort of spending years pawing through the data. So these features I've identified, the SVC, the vertical vortex sheet, the Streamwise vorticity sheet, haven't talked too much about that. These little vortices that come in, I know that some of these things have been seen in nature. The vortices have been seen with radars and also with chasers, that sometimes these vortices will show up in the cloud field. But that's a big question. And you know, I suppose for a theoretical physicist, you'd like to have a simulation and an observation, right? You know how that goes. If you have one and not the other, so we need to find this in nature, these things, in order for them to be sort of accepted as real. And I accept that, which is why I spend a lot of time working with actual field meteorologists. We're going to do more environments. If you want to read about this, we published a paper in the Bulletin in the American Meteorological Society in January. You can read about it, and I put everything up on my website too. This talk will show up on the website in a couple days with the audio if you want to look at stuff again, and you can get a link to the paper and some other stuff. But that wraps it up, so I'll be happy to take any questions.
So I'm going to ask a question first. When you've got this, you're moving your simulation so the tornado's staying sort of in the middle of your field. You must be constantly feeding in boundary conditions from the outside.
They're held fixed. That's the boundary conditions that are from the outside are the initial horizontally homogeneous base state that we imposed at the beginning of the simulation. The atmospheric sounding. We're not allowing the atmosphere base state to change. It's just frozen in time.
But are they winds?
Yep.
They're winds and stuff coming.
Winds, temperature, and humidity are all coming in from the sides. Yep, that's right. Oh, you want to do the? I'll let you pick people.
So how do you think the complexity of your simulation increase when you include terrain effects?
Terrain effects, now I've specifically tried to make this, remove as many degrees of freedom as possible in order to sort of understand these structures first. Everything matters in these simulations. When we put terrain in, it's going to change the solution. Getting terrain correct means we have to run at extremely high resolution. The Great Plains are pretty damn flat, right? They really are. If you have a valley that's like 20 meters deep, I was talking to a guy who's interested in this problem. He said, hey, there's this valley in near Moore, Oklahoma. I think it's maybe important. I said, well, how deep is that valley? He said, it's about 20 meters deep. Well, my first grid point above the ground is 15 meters. So if I tried to put a valley in, it would just be like this step function. It wouldn't look like a valley at all. But terrain is important. Getting friction right is important. Nobody gets friction right, to be quite honest with you. Nobody's getting friction right with these simulations. We're not getting it right either. But and I don't mean that sort of in a silly sense. It's hard. It's a Galilean invariancy problem, especially when you have the domain moving and you have this base state that might have some friction in it. There's some theoretical issues about handling friction, and friction and terrain are kind of tied together in my mind. So yeah, it's going to change the solution, but I don't have any generalizations to make at this point.
So how would your workflow scale up to a simulation with 100 billion or more grid points?
I love that question. So what about when I want to run on an exascale machine, right? I'll just sort of get on my soapbox for a minute. I don't care if you're a climate modeler or modeling molecules. Maybe molecules is not such a bad deal. But when you have a fluid code, you can't just do MPI anymore. You've got to do micro parallelization on these many core nodes. And when we get to these many core machines with hundreds of cores per node, we're going to have to do some more intelligent parallelization processes. Right now, the model I'm using does OpenMP. It just basically parallelizes triply nested loops with 2 threads. Everything else is MPI. That's not going to work when we have 1,000 cores per node or whatever, these many core machines. All of us modelers, when I say us, I mean those of us who do this, you really need to pay attention to the hardware and map it right. And it's not a trivial problem. Most of us meteorologists, and I imagine most of you physicists, probably aren't computer scientists as well. Many of us code. We learned how to code. We got all these bad habits over the years. We do this stuff, and oftentimes you can get a model that sort of goes into a dead end because you now have a new machine you have to map to, and you have to almost start from scratch. So what I'm saying is we all need to pay attention to we need to pay special care to the hardware when we map our problems. And it's going to be a challenge, especially as we get to many core machines. It's going to be crazy. GPUs, don't even ask me about GPUs. I mean, I love GPUs, and they have some utility, and in fact, I'm trying to get GPUs to work with fluids codes, but they're not the magic panacea. They're a pain in the butt, really, but I don't do CUDA, or OpenCL, or C++. So I'm screwed, right? Yeah. Do you have a question, sir?
How do you treat things like rain, size of raindrops, hail, dust? Does it matter?
Everything matters. Now, here's the thing. We don't actually have raindrops or hailstones. We have mixing ratios. So each 30 meter by 30 meter by 30 meter cube has one value of the cloud mixing ratio, so grams of cloud water per kilogram of dry air. So it's a mass ratio. Rain is a mixing ratio. Hail is a mixing ratio. We also forecast what's called, or we also use prognostic equation for the number concentration of those things. So we don't have we have an assumption built into the spectrum of the hailstones and the rain. There's something called a Marshall-Palmer distribution.
Does it depend on whether the raindrops or not, how big they are?
Okay, so yes, the spectrum of sizes can affect things like the terminal velocity of the raindrop. A hailstone will fall faster than like a small raindrop. If you have a lot of them, you're going to impose a stronger downdraft. That stuff is in the model, okay? But we don't have individual particles falling. It's just too much of a hard problem. You'd need a yottaflop machine? I don't know. We just don't have that capability. Dust is not in this model. Some people are using dust in their cloud microphysics in order to get the cloud seeding part right. So when you actually start to produce if I were a climate scientist, I'd have dust, okay? As a tornado scientist, dust might get in there at some point, but we don't have it in there. And it will change the solution. Everything changes the solution is the problem.
So in your typical workflow, how much time you spend on actual simulation and how much on post-processing?
Oh, good question. How much time do I spend actually running on the machine versus analyzing data? I would say that I spend about 0.5% running the model and 99.5% analyzing the output. Okay, so I've got a good allocation on blue waters, but I'll get a simulation to go and I will sit and paw through the data for a long time. Now, currently I don't have a research team so much, it's a very small team because I'm still spinning this research up, but I've got grants that are being reviewed and got grad students coming. So at some point soon, like a year or so from now, I'll be able to farm a lot of this stuff out and maybe burn more cycles. So right now, I'm in the process of, after this talk, I'm going to Oregon next week for a Blue Waters conference. Then I'm going to design some more simulations and I'll probably run on the machine for 2 weeks and then I won't run on the machine for another couple of months. That's just kind of very sporadic. So now I will say this, in order to get these lovely videos that I showed you, that took a decade of time and thinking about how to save your data, how to get it to the disk without taking too much time. I didn't talk anything about that. I use HDF5 with the core I/O driver. I buffer all my files to memory. I collect them all on a node. I build this big ass file in memory and then I flush it to disk, and supercomputers love that. So I found a way to get the data. It sounds like a trivially boring exercise, but it's crucially important. You can't just say, time to take a data dump and write 7 million files, or write one big file that takes half a day to write. So you've got to find some area between that. And I've spent a lot of time on that. Eventually I'm going to release my code to the world, and it can be plugged into pretty much any three-dimensional fluids code, so it's just, it works for me. I found something that worked, but again, right now from where I stand, most of my time is spent analyzing, which is where I want to be. I've been spending a lot of time running simulations and very little time on the machine but when the machine's running, it's doing a lot of work because I'm running on 20,000, 100,000 cores. So you would expect that the computer can, get a lot of bang for the buck, where I'm only one scientist looking at all this data, so.
Is there any upper limit to the intensity of a tornado? One thinks especially in terms of climate change and warming and warmer air with more water.
So the first part of your question, I've just read a paper that shows tornadic strength winds that are getting close to Mach 1. But those winds occur over a tiny short, like a fraction of a second. But your bigger question about essentially I think what you're asking is, can we expect more powerful tornadoes in 20 years due to climate change? There's been some research done on this. Essentially, there's two different factors that you want to look at in this kind of study. You want to look at the instability of the atmosphere with climate change, but also the wind shear with climate change. The wind shear has something to do with the gradient of temperature from the pole to the equator, and now that is getting smaller because we're heating up the Arctic more than we're heating up the equator. So the jet stream is taking all these meandering paths, which might be responsible for the weird weather we had, like really, really cold winters a couple of years ago, mostly in the upper Midwest. You guys are probably cold too. So what the preliminary results are, we're going to have less wind shear and more instability. One is going towards the direction of more powerful storms. One is going to the direction of least. So there's, at this stage, we just don't know. I think tornadoes are the least of our concerns with climate, really. If you got property in Miami, you got other concerns.
Is there any hope that at some point you would be able to say that this supercell would create a tornado, this one would not?
I hope so. That's why I'm doing this. That is the ultimate result. I mean, I might retire when that starts to happen, but yes, the whole point of this work really is that even before the storm shows up on radar, if we know from our initial conditions and sampling the atmosphere where the boundary is or something, where the storm's going to pop, we could run models ahead of the storm faster than Mother Nature. It would take a bunch of supercomputers and do a bunch of simulations, not just one, but a bunch with different initial conditions, different parameters, and run an ensemble. Run that ensemble ahead of the storm, so you got to run it in like a half an hour before the storm proves a tornado, and then you could issue a warning. What it's going to take to do that is not just computing technology, but remote sensing technology and ways to sample the atmosphere to give us the initial conditions we need. You need good initial conditions. You can have the best model in the world, but if you feed it bad conditions, it's just going to go off into la-la land. But I will say yes, it might be a long time from now, but I do believe that we can do this. We can certainly do a lot better than what we're doing now, which is we have 70% false alarm rate in meteorology. So, 3 times out of 10 when you hear the tornado sirens going off, there's no tornado. That's not a good thing. The public isn't going to say, well, I don't trust you meteorologists. And we have cases where the tornado is occurring and we don't even warn on it. Plainfield was a wonderful, terrible example of that. That storm was warned after Plainfield High School was destroyed. Oh, tornado warning, by the way. That was also a long time ago. Well, in the grand scheme of things, 25 years ago. But yes, I think we'll get there. But it's going to take a long time. Back of the room.
Most climate and weather models do not make exclusive use of or even mention the second law of thermodynamics. Does your model respect the second law? And if not, why not?
Oh, come on. Entropy. Does it respect the second law of thermodynamics? I will say maybe not to the nth point. One thing that George has been very good at with this model is he's included terms, thermodynamic terms, and I'm not necessarily answering your specific question with the second law, but the second law doesn't just show up in the model that I know. It's I know. Why not? Well, I don't know. That's a difficult question for me to answer. I don't have the actual answer for it. What we do have, essentially potential temperature is meteorologists' entropy term. So we're forecasting entropy perturbation in a sense. But that's the first, yeah, I know. Well, no, we have adiabatic, but we also have pseudo-adiabatic. We have all the thermodynamic terms. So we do the first law really good, and we do a lot of the moist thermodynamics really good. I'm not sure if we're getting the second law right or if it even matters. For these simulations.
According to Gassman, Herzog, QJRMS 2015, the fact that you're not incorporating the second law is getting the moisture transport wrong by about 10%.
I think, okay, now the 10% number makes me think this may be something that George has put in the model. He has thermodynamic terms in this model that no other cloud models have. He handles certain things much better. But I'm still not sure if it's the second law that he's doing better. So I'll let that one just go. I don't know how to put the second law into the model. I know what our equation set is, but I'm not really sure where it would even show up, so thank you, I'll work on that. No, I won't, but I appreciate the question. But you know what I might do though? I might actually go, hey George, this guy asked this really nasty question. No, and are we obeying the second law, and if not, why? And I'm interested in the answer to that question because I know what you're getting at, right? I know what you're getting at. It is, it's important. But I don't know where it shows up. It's not like in the equation set. It may be in there, but I don't know. I didn't write the model. I'll just say that. So, there was another question back in the room? Yeah.
This is an easier question. You're a good theoretical physicist. You said you appreciate data. So you can visualize a lot of detail in your models. what detail is there in real life data?
Yes.
What methods are used to collect that data?
Sure. Right now, the bleeding edge technology we have to collect data from real storms is radar. The higher frequency radars, the higher the frequency you're doing your radio waves at, the smaller the thing you can see, but the more attenuation you have. So you need to get close to the storm. So we have radar, LiDAR, in situ, which is just like, a wind vane type of thing. So we're actually measuring. So those are the basic things. Radar, photogrammetry, I mean, it's good for something. I mean, you can see what's going on. But in order to peer into the storm, you need radar. And also a good in situ sampling is useful. I think we're going to start to see probes being used more. But that's basically it. Most of it's radar. We put radars on the back of trucks and drive them to tornadoes. It's terrible. It sounds awful. I'm glad I don't do it. You hit a lot of bumps. Radar is a complex thing. You hit a few bumps in the wire, they've had all sorts of problems. Windshields get blown out. I mean, storm chasers have a really hard job, especially when you're trying to do real science. But essentially, it's mostly radar. That's the main thing for sampling inside. So radar, you get slices, right? You can slice this way, you can slice this way. You have time smearing. You don't have the full three-dimensional volume. I let the field meteorologists, I have the most respect for them, but they do that, I do this. I play with HDF, which is torture enough. They play with radars on trucks, so they have their own problems.
Can they see vortices forming in the radar data?
Yes, if you have scatterers, if you have something to scatter back, you will see a nice, beautiful couplet. You'll see one going away from you and one coming towards you. That's if you have single Doppler radar. If you have dual Doppler or triple Doppler, you can recreate the three-dimensional, you can sort of recreate the three-dimensional flow field with some assumptions built in. If you ever watch the TV news, dual Doppler, blah, 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 blah. Dual Doppler is good because you can actually recreate at least the two-dimensional winds pretty well. So yeah, you can see these little vortices. They've been seen in field data. But this simulation is just like boom. There's a lot of stuff going on, and I can't say for a fact that I know for a fact that some of the things that we're seeing have not yet been detected, or if they have been detected, we need to go back. It's sort of like the astronomers who go through those old data and try to find that that supernova or whatnot. Through stuff that's 10 years old. We may have radar data with SVCs in it. We just have to go out and find it. Good job for a grad student. So yeah, that's kind of what I'm thinking.
Okay, well, let's thank Leigh again for.
Thank you.